So, let us continue with our discussion. If you recall, we were discussing about the Lee's algorithm in our last lecture. So, we had said during the 3 steps or 3 phases of the Lee's algorithm, how we fill up the cells, how we retrace the path, and how we clear the marked cells, as well as we mark the path as an obstacle for future runs of Lee's algorithm to join 2 other points. Okay. So, let us start this lecture by analyzing the space complexity a little bit of these approaches. So, Lee's algorithm, if you recall, we looked at a problem like this where a path was retraced. Now, one thing you just try to understand from this diagram, suppose I have a source at one corner, let us say here, and my target is the other corner. So, what will be the length of the path if it exists? Let us say if there are m number of rows and n number of columns. So, you have to follow a path like this. There can be bends, but the total number of cells you have to label will be m plus n minus 1. In this case, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, it will be 6 plus 7 minus 1. Okay. M plus n minus 1, that will be the maximum length of a path between any pair of S and T, that is the worst case. All right. Okay. So, let us make the calculation of memory requirement with respect to that. So, what we are saying is that each cell needs to store a number between 1 and L, where L denotes the maximum path length that is possible. So, as I had said, for an m by n grid, I am just showing it again. Suppose I have a 2-dimensional grid with m number of rows and n number of columns, and if my source is located at one corner and the target is located at the other corner, then the length of this longest path will be like this, and this length will be equal to, as I have said, m plus n minus 1, which means, so as we are labeling the cells, this m plus n minus 1 will indicate the maximum label that I may need to use. As I number the cells 1, 2, 3, 4, 5 like that, the maximum number can be m plus n minus 1, not more than that, okay, for a problem of m by n grid, right. So, m plus n minus 1, so many numbers I have to represent. Not only that, I have to represent one unique bit combination which will denote the empty cells, and another bit combination that will denote the obstacles. So, a total of L plus 2, so many different things has to be distinguished. Now, in the binary system, if we have L plus 2 distinct things you have to distinguish and you want to represent it in binary, you need log to the base 2 L plus 2 ceiling of that many bits. So, you need so many bits to represent the state of each cell. The state of each cell can be either empty, or it can be an obstacle, or it can be a label which is numbered between 1 and this maximum L. Ceiling is what? Ceiling is the smallest number or the smallest integer which is greater than or equal to this thing. Like log to the base 2 L plus 2, ceiling means, let us say, let us take an example, let us say L equal to 3. For L equal to 3, what this value will be? L plus 2 will be 5. Log to 5 means what? Log to 4 means 2. log to 5 means 2 point something, this will be 2 point something. So, the smallest integer greater than or equal to this will be 3. So, the ceiling of this number 2 point something will be 3, but if this number is exactly 4, that means L equal to 2, then this will be exactly 2, because 2 is an integer and smallest number greater than or equal to 2 is 2 itself. Okay. So, if we say 2.15, let us say 2.15 will become, ceiling of that will become 3, right. So, this is the memory requirement for every cell in the Lee's algorithm with this kind of numbering. Now, let us take a quick look at some sample grid sizes. Say we have a 2000 by 2000 grid. B indicates the number of this L, actually L and B is the same, m plus n minus 1. So, m plus n, this 12 is the number of bit, this L plus 2, this we are calling as B, capital B. Okay. Now, it is m minus n minus 1, m plus n minus 1 plus 2, it becomes m plus n plus 1. So, m is 2000, n is 2000, 2000 plus 2000 plus 1 is 4001. So, I have not shown the ceiling, ceiling is there. If you take ceiling of this, you get 12, because 2 to the power 12 is 4096, it is less than that. So, the memory required will be so many cells, each cell with 12 bits. If you convert it to bytes, this becomes 6 megabytes. Move to 3000 by 3000 grid, your B becomes 3000 plus 3000 plus 1, log of that 13, because 2 to the power 13 is 8196, 92. So, the memory required will be 3000 by 3000 into 13, which comes to 14.6 megabytes. Go to 4000 by 4000 grid, your memory required will be, B will be 13, memory required will be 26 megabytes. So, you see that even for cells of these very nominal sizes, the memory requirement is of the order of megabytes. But if you look at practical grid sizes in the kind of VLSI chips which you have, that can be million by million, close to that. So, this number will be very huge, okay. Memory requirement will be huge. So, now we see that how we can reduce the storage requirement of the Lee's algorithm. So, some improvements. Well, before explaining this, let me just try to explain to you the basic idea behind using this numbering scheme 1, 2, 3, 4, 5. You see, in the Lee's algorithm, we are numbering the cells consecutively like this. So, there are two things that you are just ensuring here. You are ensuring that number A, the present and next cells have different levels. And secondly, for each level, let us say I mean 7. So, the cell which is just before that, it will be just one less than that, 6. So, present and previous cells, they also have different levels, but one thing is true, that you have a particular present cell, let us call it P, the next cell let us call it N, and the previous cell let us call it R. They are all distinct, they are labeled in a distinct way. Like if P is 7, the example I took here, if P is 7, then your N will be 8 and R will be 6. So, when you are carrying out phase 1 of Lee's algorithm, you know that which label to use next, and when you are retracing from 7 you are looking for a cell which is 1 less 6. So, you know uniquely which direction you have to move, right. This is one of the very important characteristics which this 1 2 3 4 5 this sequence holds. Now, the first alternative that we talk about here is that, well, here I am saying that instead of 1 2 3 4 5 6, let us say we use a numbering scheme like this 1 2 3 again 1 2 3 again 1 2 3. In this order we go on numbering the cells. Here you look at some of the properties. You take any arbitrary number, let us say this 2. For this 2, the next label is 3, the previous label is 1. They are all distinct as it was here. Take any other, let us say take 3, your previous label is 2 and next label will be 1 again, which are all distinct. So, the property of distinct numbering also holds for this. So, instead of using 1 2 3 4 5 6 in this way, I can use a numbering scheme which is more efficient 1 2 3 1 2 3 1 2 3, because in the earlier case I was going up to a maximum of L, but here I can go up to a number 3, not more than that. Okay. So, if I go to a maximum of 3, then my number of bits per cell will be log to only 3 plus 2, not L plus 2, and log to 3 plus 2 means only 3 bits per cell. So, if you look at the previous calculation here we are multiplying by 12 or 13 or 13, but in this new numbering scheme we have to multiply it only by 3. So, it will become just 1.5 megabytes, right. Okay. There is a more efficient scheme that we can talk about. Let us look at the other one. So, here I am saying that we are not even going into 1 2 3 1 2 3 like that, we are using only 2 labels. We are following this sequence 0, then another 0, then a 1, then another 1, then a 0, another 0, 1, then another 1, and so on. This is the sequence in which you are going. Now, you see here we are using 2 different colors to draw zeros and ones. A red 0 means this is the second 0 in sequence, means among the 2 consecutive 0 this is the second 0. The red 1 means this is the second 1. Similarly, blue 0 means this is the first 0 and blue 1 means this is the first one, first one. So, I can distinguish between the 2 zeros and 2 ones with respect to whether they are the first 0 or first one. I can keep track of that. When I am doing the numbering, I can always keep track of whether the number 0 that I am using, it is the first 0 or the second 0 in the sequence. If I remember that, then I can distinguish between the 2. Now, if I am able to distinguish between the 2, now you see, you take any label, let us take, I take this red 1, its previous state is blue 1, next state is blue 0. You take another state, let us say blue 1. For blue 1, the previous state is red 0, next state is red 1. So, you check for zeros also, you will find that for all the 4 cases, the previous and the next neighbors will be distinct. You can make a distinction whether they are red 0 or red 1. You see, red 0 and red 1 I am not explicitly storing, but while numbering I am keeping track of whether I am using it as the first 0 or the second 0. So, this numbering scheme will also work. I shall show you with an example. how it does, but if you can do this, this number 3 goes down to 2. So, here you need only 2 bits per cell, okay, which means in this case it is multiplied by 2, you need only just 1 megabyte. This will be only 1 megabyte in that case. Okay. So, you can reduce the storage space, but let us see how this 0011 labeling works. So, this is what I have said, 1.5 megabytes for this requires 1 megabyte. Let us take that same example, but now we are labeling with 0011. Let us start with a red 0, let us say. The source, the immediate neighbors, I am coloring them with a 0. The second 0, as a matter of convention, I am calling it a blue 0. The second 0 I label. Then I label 1, red 1, then blue 1. Then this way I proceed, red 0, then blue 0, then red 1. So, here I touch the target. Now, you see the way I label, suppose whenever I encounter a red 1, you see for red 1 the previous cell is a 0, and from that 0 the previous cell is another 0, from there the previous cell is another 1, another 1. That means, when you trace back from a red 1, you are expecting 0011, 0011 in that order the number should come. So, you see you trace back in that same order 0, 0, 1, 1, 0, 0 you reach, or you can also follow this path 0, 0, 1, 1, 0, 0 like that. Okay. So, that same thing you are distinguishing between the next level and the previous level. In this labeling scheme, if the next level is 0, the previous level will be 1. If the next level is 1, the previous level will be 0. This condition is maintained. So, you can uniquely trace back the path, and this method actually, as you can see, this requires less storage as compared to the conventional least numbering scheme. So, you get a path like this. Now, there are several heuristics, or you can say approximations that you can use in the Lee's algorithm to reduce the running time. There are 3 such strategies which are mentioned here. The first one says, so you have a pair of points, source and target, which you want to connect. Now, which one you call S and which one you call T, that is up to you, right. So, you can call the first one S, second one T, or the first one T and the second one S. Okay. So, it does not matter which one you are calling as source and which one you are calling as target. So, this heuristic says that the point which is farthest from the center of the grid, you choose it as the source or the starting point, which means, let me diagrammatically try to explain what does this mean. Suppose in this grid, so I had one point which was near the corner and one point which was say near the center, let us say here. So, what this heuristic says is that the point which is farthest away from the center, you use it as the starting point, and the one which is closer to the center, you use it as the target. So, what is the motivation? See, the motivation is simple. If you start from S, well, I am just showing the wavefronts like this, the neighbors labeled as 1, then labeled as 2, labeled as 3, like this you proceed. Okay. Then you reach T. But if you start with T, you will see that the wavefront can move in all 4 directions, like 1, then 2, then 3, then 4, like this, which means if you start with T, you will have to label much larger number of cells as compared to the case when you, what happens when you start with S. because when you start with S, you are in a corner, you are only restricting yourself to these 90 degree, the remaining 270 degree you are not propagating the waveform. So, number of cells you are labeling in this case will be much less. So, your algorithm will be running much faster, right. You see the running time will be proportional to the number of cells you are changing or you are labeling, right, because more number of cells you label during retrace phase also you will have to scan that many cells in the worst case. So, this is the first one. The second one says that, well, you generate the wavefronts from both S and T, this is called double fan out, propagate the waves from both the source and target, labeling continues until the wavefronts touch. So, let us just explain this again with the help of a diagram. Let us say I have a scenario where I have your, let us say, one point here and one point here. Let us say this is your S and this is your T. So, what this method says is that you start the wavefront propagation not only from S, but also from T. So, the wavefronts touch somewhere. So, you get a path. So, here the intuitive idea is that if you start only for one position, the wavefronts are expected to spread in all directions, but if you start from both directions, then you are not allowing the wavefront to expand in all directions. Before that, they are touching each other. So, the wavefronts are slowly expanding in their sizes and they are coming closer and closer together. So, before they expand to their full sizes and start filling up cells much more rapidly, they are touching each other, which means you are getting a path much before that. So, again here the average number of cells you will be leveling is expected to be much less as compared to the case where you start the wavefront propagation from one point. Okay? All right. Now, the third strategy is something called framing. Here what you do, you imagine an artificial boundary or an artificial rectangle just outside the terminal pairs, which is typically 10 to 20% larger than the smallest bounding box. Okay, let me again illustrate this. Let us say I have a point here and I have a point here which I want to connect. So, what it says is that you imagine a rectangular bounding box which encloses the 2 points that you want to connect, maybe like this, which is say approximately 10 to 20% larger than the smallest bounding rectangle. So, if you take these pins, the rectangle would have been this. You take a little more, because the reason is that, okay, here the idea is that when you generate the wavefronts from one point to the other, you do not allow the wavefront to cross this boundary, which means your wavefronts will only be limited to this rectangle. That means cells outside this rectangle will not be labeled. So, you are directly restricting the number of cells you are labeling, right. Now, the reason you are taking this 10 to 20% extra is that, see, within this red rectangle there might be some obstacles already existing, like there may be an obstacle like this. So, you may have to find a path around the obstacle like this. So, you are taking a little extra, about 10 to 20%, so that such obstacles can be avoided. Okay. Now, these three approaches, these are, you can say, some kind of heuristics or some kind of means intuitive approaches which try to restrict the number of cells that you are labeling. Okay. Now, in addition, of course, you can also have another scheme. You define or choose some maximum number m, you do not allow your label to go beyond m, because you know that your maximum length of the path is expected to be within m only. So, if you have an idea regarding that m, you can also take that m as a parameter. Your wavefront will not go beyond m. Okay. So, these are some approaches you can use for reducing the running time. And lastly, we consider a method or an approach in which you can extend Lee's algorithm to handle multi-point nets. Multi-point net means you have not 2, but 3 or more terminal points which have to be connected together. Now, there can be several extensions you can think of. Okay, here I am just talking about one. It says you select one of the terminals of the net as the source and the remaining as targets. Let a wave start propagating from the source till it hits one of the targets. So, you follow Lee's algorithm, you determine the path from the source to the target you have hit, and in the next step all the cells in the determined path are identified as source cells, and wavefronts are emanating from all the source cells together. So, I will show an example, and this process continues till all the targets are covered. Let us take an example like this, where I have the source here and there are 2 targets. Well, I am not showing all these steps initially. So, I am assuming that this labeling starts with S1 on 1, 2, 2, 2, 2. As you can see, T2 will be closer as compared to T1. So, S will first detect this T2 as its nearest neighbor, and maybe a path like this will be determined from S up to T2. This blue box indicates the path, right. Now, once you have identified this path, what this extension says is that all these, like here, all these cells, not only S, also T2 and also these cells which have been marked as the path, they are all identified as the source cell, and you start Lee's algorithm by numbering starting from there, like 1, 1, neighbor of this cell will also be 1, neighbor of this cell will be 1, this will be 1, this will be 1, this will also be 1. So, it is starting this wavefront emanation from all grid points along the path, not only a single point S like earlier. In this way it continues, it will be 2 like this again. So, you get this connection. So, this will be connected after that. So, this process will continue after you hit T1, this will be if there is a T3, that T3 will come next. In the next step, all these points will start emanating waveforms and T3 will be touched, right. So, this will be another path which will be identified, like that it will go on, right. So, I think in this lecture we have discussed some of the variations of Lee's algorithm which can help it to save space in terms of storage, to run faster, and also some simple way in which you can extend the basic algorithm to handle multi-pin nets. Okay. Now, in the next lecture we shall be looking at some other approaches which are more efficient in terms of the running time. Thank you.